Welcome to the webinar for TnTech's Propulsion Power and Thermal Systems Laboratory. Today we have David Schaefer, PhD student here in mechanical engineering. We'll be presenting some updates and kind of introduction to the testing capabilities we have here at TnTech for testing fuel cells. And so just to kind of, some of you may be new online and some of you new here in person, but we do these once a month where the students in the lab present their work to people that are invited. And as you will see, when you came in on the link, if you came in online, you saw the previous webinars that were given. And so they're archived and provided on the website. So you can go back and look at those, the previous ones. So we typically do these about 30 minutes and then we have questioning at the end. And so with that, I'll go ahead and let David get started.
Thank you, Dr. Roberts. Like you said, I'm David Schaefer. I'm a PhD student here at TnTech. And today we're going to go through some of the updates and upgrades we've made to our pressurized solid oxide fuel cell test stand here at TnTech. So we'll start with some background, sort of what our test stand is all about, what it does, how it works, what we use it for. And then we'll get into some of the upgrades we made over the last year, talk about some temperature gradient improvements we made, how we upgraded the test stand to be able to handle more than one fuel cell and handle a full bundle, as well as how we transitioned it into some combustor testing. And then we'll finish off with a couple future upgrades that we hope to implement before the end of the year. So first, the background of the test stand. Basically, the motivation behind the test stand is, well, to test fuel cells. But we want to test these SOFCs and SOFC-based technologies to see how they react to certain conditions and to help our models and improve our models with their performance at those conditions. So in particular at TnTech, our project's kind of focused on using fuel cells in aviation. So that's the ARPA REACH project and the NASA CLEAN project. They sort of plan for a hybrid gas turbine fuel cell system. And so we use the test stand to operate these fuel cells at conditions that they might see in such a system. For example, the pressures and fuel flow rates that it would see if it were at cruise versus if it were at takeoff. And then we sort of collect that data and help use that data to help improve our models. This test stand tests tubular fuel cells like the one pictured on the right. So this is our test stand pictured on the right here. It was built by graduate students, mostly Trevor Kramer, and then it's operated by graduate students now. And like I said, we test tubular SOFCs, and so again, pictured at the bottom, and these fuel cells are provided by SPS, or Special Power Sources, out of Ohio, so a huge thanks to them. And we usually run these fuel cells at around 750 degrees Celsius. We can vary that if we want, but that's what we operate at most of the time. And we can operate with multiple fuels. Right now we have hydrogen and methane, and we can add in mixtures of air and nitrogen as well. One of the key parts about this test stand is that it's able to test these fuel cells at pressure. And so we can test upwards of 4 bar, or roughly 4 atmosphere, and that's all controlled by a pressure regulator at the exhaust. So this is kind of the test stand if we take off that outer vessel that you saw in the previous picture. You can see that it's got a heater, which is that white cylinder in the left picture, or the orange cylinder in the CAD pictures. And then inside that heater, we have an inner vessel, or this is really like the test section. And in the very middle of that, we have the fuel cell, just being supported by the fuel inlet line. And we have a whole bunch of sensors within that test section. The bus bars are shown here, and so that's how we get our current collections and our voltage taps. But there's also a bunch of thermocouples that we can move around in there to see what's happening inside the test section. And we'll talk about that in some more slides. And then the graphic on the right kind of shows how we take it apart. So our test stand runs through LabVIEW, and it's sort of a state-based program. And so we have different states for warm up or cool down or purge or standby or hydrogen test, various things. And it's able to communicate with all of our sensors and mass flow controllers, our pressure regulator, our heaters, and then our load cells. And so it operates those and collects data from those in real time so we can view it and run our tests how we wish to run them. So the main or the key aspect of it is it has the live data collection, so we're able to see the temperatures change as we change parameters. And an important part of that as well is actually testing these fuel cells. So the main test that we run is what's called a VI curve, or it's also called an IV curve or polarization curve, depending on who you ask. And basically with these curves, you change either the voltage or the current and see how the opposite one that you changed responds to it. So in our case, we vary the current, and so we load the fuel cell with a different current and see how that affects the voltage. And so the lab view actually allows us to automate this, and so we can set what kind of step rate we want for that current to change and how long it stays at that current before it collects the data point. And then it automatically calculates how much fuel, like hydrogen or methane, it needs to send to the fuel cell so that we maintain a constant fuel utilization. And typically we run about a 50% fuel utilization. So as we're loading it more, we need more fuel to be able to handle that load, but we want to maintain that 50%. So the lab view has to tell the mass flow controllers to send more fuel. And this program also has some error and fault detection built in. It's hooked up to some safety sensors and some safety shutoffs with the gases as well. But some of the main ones is it won't let you run hydrogen below 500 degrees Celsius, or it'll warn you if it tries to flow a fuel, but then it's not actually flowing a fuel, which usually means you just forgot to open the tank or turn a valve. So that LabVIEW program collects all the data and then outputs it into some Excel files, and then we use MATLAB to analyze those Excel files, and these are just some of the examples. The graph in the bottom left is kind of the temperatures we collect along the fuel cell, and we'll talk a lot more about that when we get to temperature gradients. But the graph on the top right kind of shows some VI curves that we were running, because you can see the voltage, which is the blue line, stepping down as we were increasing current. And the graph in the bottom right shows all the different mass flows for a specific test. And you can see with the red line how the hydrogen spikes up as we go through that VI curve, and we're increasing fuel flow through that VI curve. So we also made a MATLAB app to sort of analyze these VI curves a little faster. So it can show any of the VI curves that we've previously run, any of the tests we've run. And this just allows for a quick performance comparison. So a lot of times when we're running tests now, we're like, oh, how did this compare to the previous test we just ran? And we can pull this up and be like, oh yeah, we're matching up pretty well, or maybe we're not. But it allows you to view VI curves, and you can set specific parameters like temperature, pressure, and fuel type, and sort of change between what curves and data you want to see. And it also just allows for an easier export of the data rather than the Excel files that come from the LabVIEW. Another way we're capable of testing these fuel cells is called electrochemical impedance spectroscopy, or EIS. So we have a Gamma 3000, which lets us run these EIS tests, and it helps us characterize the losses specifically at pressure. But note on the graph in the bottom right that it's a little skewed closer to the zeros because it gets the inductance of the test stand itself, but it's still able to show the transport losses through pressure, which are those circles on the right half of that graph, where you can see the 1 bar is much higher than the 2 bar. So now we'll get into one of the major upgrades we did this year. And so this was at the beginning of the year where we fixed temperature gradients. So like I mentioned earlier, our test stand is equipped with a bunch of thermocouples which read temperature along the fuel cell. And so those are shown with the 2 through 7 up and down the fuel cell there. And we would notice that we would get quite a big temperature gradient through these sensors. So the sensor at 7 might be reading 750 degrees Celsius, but the sensor at 2 would be reading as low as 680 or something like that. And so we knew this was a problem for a couple of reasons. One of the LabVIEW safety features is that you can't run a VI curve if that temperature gradient is too large because it's trying to prevent you from getting bad data. But also it increased the thermal stresses along these solid oxide fuel cells. And these tubular ones are stronger than planar ones, but it's still not something you want. And really the main driver for this was we just wanted to get better data, because it's hard to make comparison test runs at 750 degrees Celsius and 700 degrees Celsius when your tube is not at the same temperature all along it. And it also made tests hard to repeat because it was pretty dependent on how long you let the test stand kind of equalize with its temperature, because if you gave it 3 hours to warm up, it would be a smaller gradient, but if you only gave it an hour and a half to warm up, it would be a much larger gradient. And so that was always a balance of how much time we had in the day versus how equalized we let it get. In particular, we noticed that these temperature gradients got a lot worse with pressure. So you can see this in this graph in the middle. So all the squiggly lines at the top are the different temperatures along the fuel cell. And so that pink box on the left shows that temperature gradient at 1 bar. So they're all pretty close. It's about a 10 degrees Celsius temperature difference. But if you look at the red stepped line that goes across the graph, that's the pressure. And so when we step up to 4 bar, you can see that temperature gradient expands quite a bit, upwards of 60 degrees Celsius. And this is all just along a 25 centimeter tube. So that's quite a big temperature gradient. And then the picture on the right kind of shows those thermocouples and where we place them and how they measure the temperature along the fuel cells. So we usually try to keep those a centimeter or two off the fuel cell, but pretty close and consistent. So we had a few theories on why this was happening. One of them was we thought there was some sort of convective cooling happening between our inner and outer vessel. So I kind of tried to show that here through the red and blue circling lines around the heater. And so we thought the air between the vessels might be getting heated up by the heater, rising to the top, cooling, and just causing this convective path. And that in between the inner and outer vessel, we were having a temperature gradient, and that was causing the temperature gradient within the vessel. Another theory we had was just our cathode air was too cold. As you could see in this previous graph, that blue line at the bottom was the cathode air. So that's air being blown on the outside of the fuel cell. And you can see it's much lower than the operating temperature of the fuel cell itself. And so it was usually between 50 and 150 degrees Celsius below operating temperature. So the theory there was, yeah, it's kind of hard to have a good temperature gradient if you're blowing a bunch of cold air at the bottom of the fuel cell, or colder air, I guess I should say, because 600 degrees Celsius is still pretty warm. Our third hypothesis was that we just weren't patient enough with it, or we weren't giving it enough time to ramp up. So typically our ramp rate is between 7 and 15 degrees Celsius per minute. And so we go from ambient to operating within an hour and a half or so. And so this was always a balance for us of giving it enough time to equalize versus having enough time to actually run the test all within one day. And so maybe we just weren't giving it enough time for it to equalize. So we came up with a couple solutions and ideas. The first one was the easiest one to test. And so that was just slowing down those ramp rates, because we didn't have to change anything other than the way we ran the test. And while we did this, we were also changing out some gaskets to see if we were getting some bad sealing between the inner vessel and the top and bottom flanges. But then the next test we ran, we added a device to kind of block that convective cooling I was talking about. And so the center picture kind of shows those anti-recirculation donuts. And so they kind of blocked the air from being able to flow around the heater. And then our third thing we tried was a air inlet heat exchanger. And so that's shown in the picture on the right. And basically our air would come in from the bottom flange, rise to the top, and grab all the energy from the hot air up there and then go back down and then go to the cathode side. So we performed all these tests with sort of a mock fuel cell. So it was just a stainless steel tube that was the same dimensions as the fuel cell, so that we could have the same flows and same flow paths as we would with the fuel cell. The only major difference was obviously we weren't collecting any electricity off of it, and then we weren't flowing hydrogen or methane. We were just flowing nitrogen down the center of that stainless steel tube. So the first tests, we were still kind of getting organized. So the gasket tests were a little inconclusive, but the main thing we got out of them was that we were able to set up a consistent test plan. And the anti-recirculation plates were a little better, but the main thing we got out of these tests were some trends. And so that graph in the center kind of shows that. And so the gray bars and the yellow bars are the same test. It's just whether we were upscaling pressure, so going up from 1 bar to 4 bar, or downscaling pressure, going from 4 bar down to 1 bar. And you can see the yellow bar is much smaller temperature gradient than the gray bar. And so we figured maybe that's because we're giving it more time, because it's already had to get up to pressure. And then when it's going back down to pressure, it's had more time to equalize. And so you have a lower temperature gradient. And then the blue and green bar are when we added those anti-recirculation kind of donuts. And so they improved, especially on the going down in pressure, but there was still quite a bit of temperature gradient, like upwards of 50 degrees Celsius at 4 bar. Another trend we noticed with this was that there was a pretty strong correlation with the inlet temperature of the cathode. And so this graph is kind of the opposite of the other graph, where now with the downscaling, you have higher values for the temperature in the cathode inlet. And so that kind of took us along the path of maybe as we wait longer, our cathode inlet temperature gets higher, and then that makes the temperature gradient better. And so that's what led us to test that cathode inlet air heat exchanger, because we were trying to warm up that cathode air to see if that would fix temperature gradient. So that's where this design I talked about earlier comes into play. And so another important thing to note with this is that because we only use 50% of our fuel, that means we have a lot of hot hydrogen or methane or mix of hydrogen and other gases coming out the end of the fuel cell at the top there. And so right as that's exposed to oxygen, because we're at such a high temperature, that auto ignites. So we wanted to take advantage of all that heat at the top with that heat exchanger. And then we also wanted to distribute that that air that we were sending in on the cathode side evenly around the fuel cell. And so that's where we have this distribution ring or shower head, which you can see in the picture in the bottom left, kind of that little ring with the holes in it, or the blue ring in the CAD pictures may be easier to see. Yeah, I was gonna, let's see. So this sort of ring here, you can see that's like an outlet there and an outlet there, and it goes all around the fuel cell. So we were actually shocked at just how well this worked. And so this was one of the tests we ran after this. And if you remember that graph I showed earlier where we had the steps in pressure and how the temperature gradient kind of went crazy, the graph on the right here shows the opposite. Like you can barely tell that we were up in pressure at all because the temperature gradient and the temperatures just stayed so close to each other. And we were actually running VI curves through here, and you can't even tell through the temperatures, which is something we were able to do before. And the graph on the left just shows how we were getting a consistently higher cathode inlet temperature. It's still off from the fuel cell temperatures, but much better than what it was before. So one of the next big modifications and upgrades we made to the test stand was making it capable of testing this 25 tube bundle. So this was for the RPE REACH project. So it was kind of a big shift because instead of testing one fuel cell, we were testing now 25 fuel cells, and there was a combustor added to it. So obviously with the more fuel cells, we had to throw a lot more air and a lot more fuel into it. So we had to make upgrades to those mass flow controllers and those lines. And we actually had to get sort of a backup air compressor to help assist the air we were getting from the building air compressor in times of like high loading, and sort of as just a backup just in case. We had to adjust the lab view a bit because it was designed to handle one fuel cell, and so things were a little bit different with 25 fuel cells. One major difference was the lab view had like a safety shutoff where the voltage got below, I think it was 0.5 volts or so, because it didn't want you to load the fuel cell too hard. But now, if you got 25 of these in series down to 0.5 volts, you would be doing quite a bit of damage. So we had to adjust that. And then we also had to implement a little bit of structure because we can't exactly hold 25 tubes up with the fuel line like how we were holding the single tube up with just its fuel line. So with sending so much more mass into it, we also had to upgrade the exhaust so we could get all that mass back out. And so most of this was driven by the pressure regulator. And so it has limits of temperature. It can't go above 60 degrees Celsius because that's just what it's tuned for and what AliCat recommends. We also had to prevent water and liquids from settling in the regulator. And as we learned through our first bundle test, 25 fuel cells produce quite a bit of water. So we added a coil heat exchanger and a water dropout system. So the exhaust comes out about here and then goes up and around this coil heat exchanger. And so that just reduces the temperature with the ambient air. And then it goes into this, it's kind of hard to see, but there's a heat exchanger with a water chiller laying horizontal here. So that water would be at like 5 degrees Celsius. So that would, again, just help to cool down the exhaust. And then this was also put on slightly slanted so that if we did condense any water, it would flow into our water dropout system here. So this water dropout system is these two tanks, and they're built in a way that we can take the water out even when we're at pressure. So that's why there's a combination of tanks and valves there. And then it exhausted through the pressure regulator and out to the fume hood. So some of the bundle testing results. The first test, it was just good to get it going. Good to find the little quirks and kinks in the LabVIEW program. Like some of the gas calculations had to be modified a little more for the automated VI curves, but nothing major. And then we actually found an interesting use for our thermocouples because they were able to detect leakage because they would heat up in certain areas where we would start leaking hydrogen through the bundle. And so we could tell, oh, hey, we're leaking, or we've really moved the combustion out of the combustor somewhere else. And so a big thing that came out of the first test of this was that we needed to kind of improve our combustor knowledge. And so that kind of led into the next big upgrade and testing we did this year, which is combustor testing. So in a perfect world, or if you say hindsight is 2020, we should have done this beforehand. But in the last month or so, we've been testing combustors to try to get better understanding of them so that we can better implement in that bundle and test that bundle and combustor combination again, and hopefully get better control over it. So this cat on the right is the combustor we're actually about to test next week. But we just want to understand what conditions allow for combustion, what sort of flow rates, what sort of temperatures and pressures, and just understand the combustor so that we can implement it with the bundle and then try to understand the two together. And so this next test, we're trying to simulate the conditions of the bundle. So that's why we have that plate at the top here. That's supposed to simulate the bottom of that bundle. So we ran one test on just a combustor, and we actually found some pretty useful data from it. So you can't really see, but on this bottom plate, you have a fuel line coming in and then an air line coming in. So one of the major things we found with this test was that because we flow so much more air than fuel, that air kind of dominates the fuel and sends the temperature off to the side. And in this case, I think it was the 6 o'clock thermocouple. And so you could see that there's a even greater temperature gradient than what we were talking about earlier, because there's a 100°C difference between a couple inches apart of this combustor. And so this led to some design improvements that we implemented actually in this combustor design, where we have the fuel and air coming in at one spot to hopefully mitigate that. But this was also our first use of a mass spectrometer that we got. And so we just set the mass spectrometer up to read the exhaust at the fume hood. So we knew we wouldn't have any liquids or high temperatures or anything crazy. But it was cool because we could tell when we weren't combusting things because we would read a lot more hydrogen. So this blue spike here is an atomic mass of 2, so H2. So we were getting hydrogen out there and we weren't combusting it. So that was pretty interesting to see. But that kind of leads into the coming upgrades that we want to do over the next few months here. And so the first one is to better understand that mass spectrometer. So we have a Haydn benchtop gas analysis system. And that first combustor test was a great sort of getting our feet wet with the mass spectrometer, but we want to do a little more with that. And ideally, we'd actually use some capillary tubes and implement this within the test section so that we can see what sort of gas compositions we have at different parts along the fuel cell. And so this could be good for other fuels. It could also be used to detect leakage potentially, but we'll see. And so we're still learning on that one. Another big future upgrade is to implement ammonia. So specifically for the NASA Clean project, they want to utilize ammonia for their hybrid gas turbine fuel cell system. And this is because they want to use it as a hydrogen carrier because it's more energy dense, but it still doesn't have any carbons like methane does. But if you know anything about ammonia, it's that it's pretty toxic. So most of our upgrades to the test stand are safety related. So we're going to store the ammonia and all of its mass flow controllers and valves, or as much of it as we can, within a fume hood, so that if there is any leak, we're safe from it. And of course, we had to get the appropriate PPE, which is shown on the picture on the right. And then we also got a safety shower just in case. And then we have a bunch of detection devices and sensors that we'll be getting in the next coming month or so. And then another big change is now we have to test the test stand remotely. So we're going to be running it from the hallway rather than running it from right beside it. And another upgrade we plan to implement is the ability to test jet fuel. And so this just adds to our capabilities and what fuels we can test and hopefully compare between the fuels. But jet fuel is kind of a whole different beast just because this is our first attempt at a liquid fuel. So we'll have to do some modifications to the fuel before it even gets to the test stand. It's also our first more, you could say, traditional fuel. It's kind of used every day versus hydrogen is not always used everywhere. And to start with, we're just going to use desulfurized jet fuel to kind of simplify the process, but eventually we may run into having to desulfurize our jet fuel before the test stand. We're hoping to run this test before the end of the year. And it may be just a simple test, hopefully to get it stable at a sort of operating condition. And so basically through this year, we've been able to help perfect our test stand a bit, get those temperature gradients right and improve on it and upgrade its capabilities so we can test more than just one fuel cell, so we can test more than just hydrogen and methane. And I guess by the end of the year, we'll be doubling our fuel capabilities. So that'll be good. And it'll just allow us to test fuel cells at all sorts of different conditions with different fuels and get better comparisons and characterizations between them. And a big thanks to, like I said earlier, SPS for providing the fuel cells, and then ARPA-E and NASA Clean for providing a lot of the funding for this test stand. Thank you guys. Do you have any questions?